A theory of everything or final theory, ultimate theory, or master theory is a hypothetical single, all-encompassing, coherent theoretical framework of physics that fully explains and links together all physical aspects of the universe. Finding it is one of the major unsolved problems in physics. Over the past few centuries, two theoretical frameworks have been developed that, as a whole, most closely resemble it. These two theories upon which all modern physics rests are general relativity and quantum field theory. GR is a theoretical framework that only focuses on gravity for understanding the universe in regions of both large scale and high mass. Stars, galaxies, clusters of galaxies, etc. On the other hand, QFT is a theoretical framework that only focuses on three non-gravitational forces for understanding the universe in regions of both small scale and low mass. Subatomic particles, atoms, molecules, etc. QFT successfully implemented the Standard Model and unified the interactions between the three non-gravitational forces, weak, strong, and electromagnetic force. Through years of research, physicists have experimentally confirmed with tremendous accuracy virtually every prediction made by these two theories when in their appropriate domains of applicability. In accordance with their findings, scientists also learned that GR and QFT, as they are currently formulated, are mutually incompatible. They cannot both be right. Since the usual domains of applicability of GR and QFT are so different, most situations require that only one of the two theories be used. As it turns out, this incompatibility between GR and QFT is only an apparent issue in regions of extremely small scale and high mass, such as those that exist within a black hole or during the beginning stages of the universe. To resolve this conflict, a theoretical framework revealing a deeper underlying reality, unifying gravity with the other three interactions, must be discovered to harmoniously integrate the realms of GR and QFT into a seamless whole. A single theory that, in principle, is capable of describing all phenomena. In pursuit of this goal, quantum gravity has recently become an area of active research. Over the past few decades, a single explanatory framework, called string theory, has emerged that intends to be the ultimate theory of the universe. Some physicists believe that, at the beginning of the universe, the four fundamental forces were once a single fundamental force. According to string theory, every particle in the universe, at its most microscopic level, consists of varying combinations of vibrating strings with preferred patterns of vibration. String theory claims that it is through these specific oscillatory patterns of strings that a particle of unique mass and force charge is created. Initially, the term theory of everything was used with an ironic connotation to refer to various overgeneralized theories. For example, a grandfather of Ijon Tichy, a character from a cycle of Stanislaw Lem's science fiction stories of the 1960s, was known to work on the general theory of everything. Physicist John Ellis claims to have introduced the term into the technical literature in an article in Nature in 1986. Over time, the term stuck in popularizations of theoretical physics research. Historical antecedents. From ancient Greece to Einstein, Archimedes was possibly the first scientist known to have described nature with axioms and then deduced new results from them. He thus tried to describe everything, starting from a few axioms. Any theory of everything is similarly expected to be based on axioms and to deduce all observable phenomena from them. The concept of atom, introduced by Democritus, unified all phenomena observed in nature as the motion of atoms. In ancient Greek times, philosophers speculated that the apparent diversity of observed phenomena was due to a single type of interaction, namely the collisions of atoms. Following atomism, the mechanical philosophy of the 17th century posited that all forces could be ultimately reduced to contact forces between the atoms, then imagined as tiny solid particles. In the late 17th century, Isaac Newton's description of the long-distance force of gravity implied that not all forces in nature result from things coming into contact. Newton's work in his Principia dealt with this in a further example of unification, in this case unifying Galileo's work on terrestrial gravity, Kepler's laws of planetary motion and the phenomenon of tides by explaining these apparent actions at a distance under one single law, the law of universal gravitation. In 1814, building on these results, Laplace famously suggested that a sufficiently powerful intellect could, if it knew the position and velocity of every particle at a given time, along with the laws of nature, calculate the position of any particle at any other time. An intellect which at a certain moment would know all forces that set nature in motion, and all positions of all items of which nature is composed, if this intellect were also vast enough to submit these data to analysis, it would embrace in a single formula the movements of the greatest bodies of the universe and those of the tiniest atom. For such an intellect, nothing would be uncertain and the future just like the past would be present before its eyes. Essai philosophique sur les probabilités. Introduction. 1814 Laplace thus envisaged the combination of gravitation and mechanics as a theory of everything. Modern quantum mechanics implies that uncertainty is inescapable, and thus that Laplace's vision has to be amended. A theory of everything must include gravitation and quantum mechanics. In 1820, Hans Christian Ørsted discovered a connection between electricity and magnetism, triggering decades of work that culminated in 1865, in James Clerk Maxwell's theory of electromagnetism. During the 19th and early 20th centuries, it gradually became apparent that many common examples of forces, contact forces, elasticity, viscosity, friction, and pressure, result from electrical interactions between the smallest particles of matter. In his experiments of 1849–50, Michael Faraday was the first to search for a unification of gravity with electricity and magnetism. However, he found no connection. In 1900, David Hilbert published a famous list of mathematical problems. In Hilbert's sixth problem, he challenged researchers to find an axiomatic basis to all of physics. In this problem he thus asked for what today would be called a theory of everything. In the late 1920s, the new quantum mechanics showed that the chemical bonds between atoms were examples of electrical forces, justifying Dirac's boast that the underlying physical laws necessary for the mathematical theory of a large part of physics and the whole of chemistry are thus completely known. After 1915, when Albert Einstein published the theory of gravity, the search for a unified field theory combining gravity with electromagnetism began with a renewed interest. In Einstein's day, the strong and the weak forces had not yet been discovered, yet he found the potential existence of two other distinct forces, gravity and electromagnetism, far more alluring. This launched his 30-year voyage in search of the so-called unified field theory, that he hoped would show that these two forces are really manifestations of one common underlying principle. During these last few decades of his life, this quixotic quest isolated Einstein from the mainstream of physics. Understandably, the mainstream was instead far more excited about the newly emerging framework of quantum mechanics. Einstein wrote to a friend in the early 1940s, "I have become a lonely old chap who is mainly known because he doesn't wear socks and who is exhibited as a curiosity on special occasions." Prominent contributors were Gunnar Nordstrom, Hermann Weyl, Arthur Eddington, Theodore Kaluza, Oscar Klein, and most notably, Albert Einstein and his collaborators. Einstein intensely searched for, but ultimately failed to find, a unifying theory. More than a half a century later, Einstein's dream of discovering a unified theory has become the holy grail of modern physics. 20th century and the nuclear interactions in the 20th century. The search for a unifying theory was interrupted by the discovery of the strong and weak nuclear forces. which differ both from gravity and from electromagnetism. A further hurdle was the acceptance that in it, quantum mechanics had to be incorporated from the start, rather than emerging as a consequence of a deterministic unified theory, as Einstein had hoped. Gravity and electromagnetism could always peacefully coexist as entries in a list of classical forces. But for many years it seemed that gravity could not even be incorporated into the quantum framework, let alone unified with the other fundamental forces. For this reason, work on unification, for much of the 20th century, focused on understanding the three quantum forces, electromagnetism and the weak and strong forces. The first two were combined in 1967–68 by Sheldon Glashow, Steven Weinberg, and Abdus Salam into the electroweak force. Electroweak unification is a broken symmetry. The electromagnetic and weak forces appear distinct at low energies because the particles carrying the weak force, the W and Z bosons, have non-zero masses of 70018040000000080.4 GeV, C2 and 700191200000091.2 GeV, C2, whereas the photon, which carries the electromagnetic force, is massless. At higher energies, W's and Z's can be created easily and the unified nature of the force becomes apparent. While the strong and electroweak forces peacefully coexist in the standard model of particle physics, they remain distinct. So far, the quest for a theory of everything is thus unsuccessful on 2 points. Neither a unification of the strong and electroweak forces, which Laplace would have called contact forces, has been achieved, nor has a unification of these forces with gravitation been achieved.